very, very short, quick bullseye. Last time. Ellipses. All right, here's the bullseye. And we had this other bullseye at the beginning of the semester, that had regular sets in the middle and context-free languages outside of that, and decidable languages outside of that, and then undecidable and then not partially decidable. And it's like they're two separate diagrams. I never drew them on the board at the same time, for fear that they would insult each other or something. But the truth is, they have to fit in with one another. So where do they fit in? Where do regular sets fit in this diagram? Where do context-free languages fit in this diagram? Where does the decidable languages fit in this diagram? So let's start with the easiest question. If I drew a circle to represent decidable languages, where would it be?
Around the whole thing.
Around the whole thing, inside P, in P space, where would it be? Every one of these classes represents Turing machines that solve problems in this amount of time. So they all are guaranteed to halt in these time or space bounds. So decidable languages go out here. All this complexity theory stuff is underneath the decidable languages. Now, what about languages that are context-free? Sets of strings that could be generated not by a Turing machine, but could also be generated by a context-free grammar. Everyone understand? It's hard to decide that, but let's say somebody gives you a grammar and says, here's a grammar, and you know that the set of strings is from that grammar. How much time would it take for you to write a Turing machine, or how much time would the Turing machine take once you wrote it to accept all the strings in that set? That's the same question as how much time does it take to solve the membership problem for context-free grammars? You're given a string, it comes from a context-free grammar, you're going to write a program now to decide it, not a push-down machine, a program. How much time does it take?
Linear.
Right, the best time we know is linear, for deterministic context-free languages at least. For non-deterministic, we have this algorithm we did in class, which is the order n cubed in the worst case. So all those context-free languages are way inside here, CFLs. And in particular, they're n cubed or less. Okay, so they're way inside. Now what about regular sets? They're even further inside. How long would it take your program to recognize strings that were regular sets? More or less linear time. It just scans the input going from state to state and it knows the answer. Okay, so the book actually mentions a nice result about that. The book talks about Turing machines that try to accept this, right? And it gives you one method that takes order n squared. Just a completely random method takes order n squared. You find the matches, you go to the next match, you might scan the whole thing n times. That gets order n squared. And the book tells you a more clever way to do it. They figure out a way to do it in n log n. You can think about that yourselves, how you might want to do this on a Turing machine in n log n, so that you don't actually scan all of it n times, you scan all of it at most log n times. It's not too tough. Think about it. You can figure it out. Look it up in the book if you can't figure it out. Then the book mentions, and it's kind of a neat theorem, he doesn't prove it, he says, and I don't ever expect to do any better than this. And I don't ever expect to do any better than this because this is not a regular set. And it's known that you can't do better than n log n for things that aren't regular sets. Regular sets can be done in linear time. Okay, but you shouldn't expect to do better in general. All right, he talks a little about that. But generally speaking, all I want you to know is that regular sets are in here, context-free languages, polynomial time, etc., decidables out there. So complexity theory is a long discussion about what happens in between here and here, and then spreading those classes out. It's like a big magnifying glass. Just a little hole I wanted to mention. I want to make sure you all knew this, and I don't think there's any other things that we really missed out. We didn't spend a lot of time talking about particular reductions because we did spend a lot of time talking about that in algorithms. And I didn't want to just redo it again because they can get very, very complex and sometimes tedious. But I did give you problems on it because I think they're fundamental to this topic. So you should work on them. If you can't get them, ask me. I'll help you get them. And And that'll end problem set 5. I also decided tomorrow we have the final exam for this month, and I want everybody to finish by 3 and then go away and have a good time over the weekend. You can hand in problem set 5 when you come back on Tuesday if you like. That's okay. But I want the exam to be in my hand so I can grade it over the weekend. So in order to do that in the way that will make it best, none of you are going to concentrate if I do a lecture tomorrow morning anyway. So I'm just not going to do one. You can come in 9:30, start the exam then, but be done by 3. You can also come in 1 o'clock and be done by 3. Okay? It's meant same time as last. Same duration. Okay. Questions? All right, so now I'm ready to shift over. Sometimes called the recursion theorem. Sometimes in more mathematical books it's called a fixed point theorem. Now, of all the things we've done this whole semester, every single one, whether you like this stuff or not, does have completely practical applications in computer science, both theoretical and real life. This is just more of a curiosity. You can find a gazillion web pages that talk about it because it's a really cool curiosity. But the main curiosity that this implies is that programs are powerful enough to be written so that they can, as part of what they do, write descriptions of themselves out into memory. They can do more than that, but part of what they can do is actually know about themselves, know their own description. That's basically what this says. I will tell you specifically what it says in a little while, but I want to give you some intuition about it. The reason I'm giving you intuition, I found this great quote, which I thought about a long time before I decided whether I was going to do this lecture or not. I thought maybe I'd just do something else that would be easier to understand or more fun. And then I found this quote, and it really made me think that. This is by Juris Hartmanis, who's at Cornell, who's one of the pioneers of complexity theory. Worked on it from the 60s up through, he's probably even active today in research. He says, the recursion theorem is like tennis. Unless you become exposed to it at age 5, you will never become world class. So I thought about this, and I'm thinking, well, I'll just teach it to them in 45 minutes. That'll be no problem. And then I thought, is he right or not? And actually, I think he's right in some sense, that this is not something you see once and say, okay, now I get it. It's something you see once, and then it has to kind of seep in. And you get it better and better and better every year of your life. And if you started seeing it at 5, it's like these little kids who can play with a mouse very early. It's like part of their hand. They get muscle memory. This is kind of like, I don't know what kind of memory it is. But then I was passing by Greg in the hall, and he goes, yeah, but how many people really want to become world-class experts on recursion theory? And I said, well, that's true. Probably none of you do. So I figure you're not going to become world-class experts if you see it when you're 30. But you'll certainly get enough of a sense after today of what this is really about and what it implies. Because we're going to start with this very abstract description about Turing machines, but then we're actually going to go and take the implication of that abstraction, one of which is that programs can actually output themselves. You run the program and the output is the program. You've all told me that you read a paper about this in systems. So the programs that do this in some languages are longer than others, depending on what the language lets you do. But I looked at dozens of these. There's a web page that has these self-producing programs or printing programs, self-printing programs in hundreds of languages. And the one that I thought was most clear, but still captures the flavor of it all, and pretty much follows the abstract discussion in Turing machines, is one that's written in a language that I know well, called Logo, which is like a dialect of scheme. So I brought my little Logo interpreter on my laptop here today. We're going to write this program on the board in Logo, taking the abstract Turing machine explanation as our motivation, using that to help us write the program, and then we'll actually look at it and see what it does. I also pulled out a C version for those of you who are a little more traditional, and it's very similar to the Logo one, but a little more obscure, so I didn't like it as much. But I'll show you how that works too. All right, so we'll do that later, but now we first need to talk about what's really going on. I should mention that this this peculiarity of a program that actually outputs itself, that is one implication of the recursion theorem. It is not the whole recursion theorem in its complete glory. It's one particular piece of it. Let me give you another little piece of the recursion theorem and give you a sense of why it's called a fixed point theorem, and show you how this connects with the real theorem a little later. But imagine this, just for a moment. And here's why the recursion theorem is called a fixed point theorem. Imagine you were writing a Turing machine or a program whose job it was to take other Turing machines and simulate them on a particular input, say the string 0. Okay, we'll call this the sim on 0. Looks like my name. Sim on 0 Turing machine. Okay, so here's what it's supposed to do. It's supposed to take another input that represents somebody else's program, and it's supposed to simulate that program as if that program was given the input 0. Everyone understand what it's supposed to do? All right. So this Turing machine that simulates other programs on 0 is going to have a bunch of states. It could be represented itself by some string. Do you think it's likely that the string that represents this program is actually the single symbol 0? Probably not. It's probably some long, complicated string. Okay? There's another program, simulate on this program also takes Turing machines as input, and it simulates them on this string. And whatever the Turing machine that it takes in as input does on this string, that's what this Turing machine will do. It'll just simulate it on this particular string. It takes any machine, simulates it on this particular string. So here is a corollary or an application of the recursion theorem or the fixed point theorem. The recursion theorem implies that there's some string that when you write the simulation on that string, that the description of the Turing machine that does the simulation is actually the string itself. Everyone understand that strange thing? Remember I told you we don't think that this simulation is going to be represented by the string 0, nor does this simulation program likely to be represented by this short string. But the fixed point theorem implies, or the recursion theorem implies, that if you write a whole bunch of these programs that simulate other Turing machines on particular strings, that one of those programs, if you look at its description itself, will actually be the string that the other machines are simulating it on. So it's a fixed point theorem because sooner or later, one of these programs that's trying to do one of these tasks is going to be the string itself that the other thing is simulating on. In other words, the Turing machines that it takes in are actually being simulated on itself. Fixed point because this little part ends up being the same as the machine itself. All the others might be different, but one of them, it's going to match. Right. Is that already a little too weird? We have no idea which string it's going to be, but you could find it if you looked hard enough. All right, those are some of the implications of the fixed point recursion theorem. But some of the more easy to see, appreciate, and understand are the ones where the machine just outputs itself. So let's start with that. And our book does the same. It starts with that, and I think it's a good idea. So, before we talk about this recursion theorem or more implications of it, and I'll get back to that other implication later, let's talk about viruses, or basically programs. These are a little simpler than viruses, programs that print themselves. Basically, viruses are programs that print themselves and probably do something nasty also. And then print themselves, and then they spread. They do nasty stuff and spread themselves. Okay. So we need to prove that there's a way for a program to print itself. And I don't know. Does anybody feel like that's easy? Because every time you try to do this, it ends up being hard. And here's the way typically you start. Print F. Well, I don't know. Print F. Print hello world. All right, so this prints hello world. Let's try to make a program that's going to print this program. because this doesn't print itself, just prints part of itself. So let's make one that prints this. Main print. You don't have to know too much C to try to do this. What should go in these quotes if we're going to try to print this program? Main, parentheses, open brackets, printf, hello world. Now that doesn't quite work because I want to actually print these quotes, right? So I kind of escape those quotes so that it doesn't end this quote. You all know that you have to do that, otherwise it ends the quote. So I escape these quotes out, so it actually prints those quotes. Semicolon, close bracket, close quote, parenthesis, semicolon, close bracket. All right, so what does this do? This program prints this program. And you can easily convince yourself that this is just hopeless. I can make a program that prints this one now, and then another program that prints that, and I could easily say, this is just like everything we ever do, right? Anytime you have something in the same city, the actual members of that city are not smart enough to know about everything about their own members. You have to have somebody outside the city who's smart enough to really, really understand everything in the city. But that's not going to be true here. A program is clever enough to print itself out. And it does not connect to the idea of somebody in town being able to do something for everybody. And it feels like it might, but it doesn't. But we need a better strategy than this. This is one rotten strategy. So let's kill this strategy and talk about a strategy that works. But we're going to talk about a strategy that works not in terms of a real programming language, but in terms of Turing machines, which is where this proof really comes. And you don't have to take notes on this because the book writes this up in very nice detail and explains it. But I'm just going to explain it here again. Here's the plan. We're going to write a Turing machine called self. And the job of this Turing machine is to print itself out. That's all it's going to do. Remember, every Turing machine has a description of itself, some sequence of zeros and ones that represents that Turing machine. Just as far as notation goes, if we talk about what a Turing machine does, we might give the Turing machine a name. We might call it P. And we say P computes this and this and this. And if we ever write this, we mean the encoding of P. We mean the zeros and ones that represent that program that we're talking about. Right? So let's distinguish between this and this. This is the machine, and I'll talk about what it's doing, what it computes, and angle brackets P is the actual encoding of P into a string. And it seems like a minor thing to make a fuss about, but there won't be any way to describe what we're doing unless we distinguish between these two. Okay, questions so far? All right. So here's the trick. This TM called self, here's the description of it. It's going to be composed of two other pieces. Think of this as meaning that self has two parts, an A part and a B part. Very abstract here, but in just a couple minutes you're going to see these parts show up in a real program, so it won't be so weird. Self has two parts, A and B. I'm going to describe each of the jobs of these parts, but basically here's what's going to happen. A is basically going to look at B and store B in memory, or put B on the tape. And you're thinking, well, what the hell is B? Well, I haven't told you that yet. But whatever it is, A is going to put it on the tape. Now what B is going to do is really weird. B is going to look at the tape that A wrote the description of B on. It's going to look at it, say, here's a description of me. And now I'm going to compute what I'm supposed to do, and then put that on the tape, and then put A in front of it. Let me write it out in more detail. It'll make a lot more sense when I do it in a real programming language. You really see how it works. Here it's going to be a little bit wild. So let's do it anyway. All right. Here's what A does. Oh, I need one little more piece of notation. I'd like to avoid this, but maybe it's best not to. The book puts this in as a lemma, and it really is something that makes the description easier to do. So maybe I should do what they do, because otherwise somewhere along the way I'm going to need this word and I won't have it, and I better do it now. The book has something called Q. Q takes a string W. And here's what it does. It does something really simple. It's not complicated. It's just some notation for describing things easier. Q is a function that takes a string W. And it outputs a Turing machine that does nothing but print W as output. Okay, so Q of W is a Turing machine that outputs W.
Does it do it for all W's, whatever it is? It's just a machine that...
It's just a machine that does nothing but output W. It's a fixed machine. You can put anything into this machine. All it's going to do is output W. If I do Q of 0, 1, then that's a Turing machine that just outputs 0, 1. You're going to think, why do I need this notation? You'll see in a second. What if I stick a Turing machine into this Turing machine? What if I stick in a description of a Turing machine called A? This is a weird thing to do, but I could do it. I put a big string in here. Then this produces another Turing machine that does nothing but output the description of the Turing machine A, the encoding of A. All right? That's all it does. It's another Turing machine, not A itself. It's a Turing machine that outputs A. Everyone understand what Q does and how we might use it? We're going to use it right now. Yeah.
Yeah, that's my question. Is Q the Turing machine, or does Q a function that generates a Turing machine?
Q is that Turing machine. Q of W is the Turing machine that outputs W. Yes. Yes. OK, so here's what A does. Here's A's job. A saves Q of B on the tape. In a program, what it does is save this in memory. Now, before I go on, what does this mean? It means it makes a Turing machine that does nothing but output the encoding of B, and it puts that Turing machine on the tape.
The encoding of that Turing machine.
The encoding of that Turing machine on the tape, right.
Should be also correct.
No. It puts that actual Turing machine on the tape. Well, the encoding of that Turing machine, fine. Q of B is the encoding of that Turing. Oh, that's what you asked me here? Is this the Turing machine or the encoding of the Turing machine? Is it? It puts on the tape an encoding of a Turing machine whose job it is to do nothing but print out the description of B. Now, the thing is, we don't know what this should do right now because we don't know what B is. So let me explain what B does. So hold off, because we can't really finish this step or know the details until we do this. But once we do know this, we'll be able to take the encoding of what B does, create a Turing machine that prints that encoding, and put it over here. Oh, you really need to see a program that does this. But let me finish this first. All right, so here's what B does. Get the output of A from the tape. It goes ahead on the tape and looks at whatever A outputted. In other words, what is it getting from the tape? It's getting its own description. This is a key part. It's looking at the tape and finding its own description, something that says how it works. And it computes. It actually computes this. And in a language, this is usually a 2-second step, usually putting brackets or quotes around something. It computes Q of B, which equals A. And I'll make a comment. That's a program that prints out B. Okay, so it computes this. It looks on the tape and finds a description of B. It computes a Turing machine that's supposed to print that description out. It can do that because any Turing machine can compute Q of another Turing machine. And now that it's got this, now it's figured out A, here's what it does. It prints out that A followed by the B. You got to think this is hocus pocus, because it just doesn't look like it means anything. But it really does. And the best way for me to describe to you what it means, instead of sitting here and running through the semantics of this and going back to Q and unraveling it, it'll just tie your neurons in a knot unless you've had 10 years to think about it. Look at it. It's accurate. It's really right. But you'll appreciate why it's right if I show you how to do it in a language rather than on a Turing machine. All right, so let's do that in parallel to this. I will mimic this plan in Logo. Logo isn't too hard to understand. I'll explain the details of it as we go. I'll mimic this in Logo. It'll be a 3-line program, and we will have it work just because we followed this strategy. And then you'll probably learn what this strategy means more by the example than use the example as a particular case of this. You probably don't get this yet, but you will get it when you see the example. All right, so questions before I go on. In parallel to this, I will mimic this plan in Logo. Logo isn't too hard to understand. I'll explain the details of it as we go. I'll mimic this in Logo. It'll be a 3-line program, and we will have it work just because we followed this strategy. And then you'll probably learn what this strategy means more by the example than use the example as a particular case of this. You probably don't get this yet, but you will get it when you see the example. All right, so questions before I go on. Ready to see this example? Then maybe ask a question? All right. So this example is in Logo. We're going to write a self program in Logo. Now in Logo, when you write a procedure, you start it with a word to. So here's the procedure. To self. And here's end. That ends the procedure. All right? Ooh, now what goes inside? There's only 2 lines, and it's going to write itself. It's so cool. It's the coolest thing. I had so much fun playing with this last night. All right.
Are you exposing your kids to this?
No, I just kicked them downstairs. I said, leave me alone. I got to think.
Any 5-year-olds?
This is so hard to think about.
Do it. Otherwise, they'll never be in one class.
That's right.
Oh, I see. Well, one of them's not 5 yet. Maybe I should expose him to it. He's only 3. Forget world class. We're talking about universe class. I could teach him the words recursion theorem. That would make him quite a conversationalist. All right. The first thing we do, part 1 of this program, is write some piece of code that saves the description of the second part of the program onto a tape. So here's what that looks like in Logo. You make a variable. Let's call it x. And we don't have tapes in Logo. We have memory. And x is a variable in memory. So we're going to save this description in memory. And we're going to save it in a place called x. So it looks like this. Make x. And right in here, where's my colors? Let's go for purple. Right in here will go the description of B. But I can't put it in yet because I don't know what it is. That's exactly how you should write one of these programs. You store what the program is going to be further down, and then you write the program further down, and when you're done, you stick it back in here. Okay, that's just what this is telling you to do. To make it a little more sense, but not yet, right? We have to go on. Okay. So what is B supposed to do? B is supposed to get this output A from the tape. How does it do that? It refers to this memory variable, x. Now in Logo, if you want to get the value of a variable called x, you put a colon in front of it. Dots x, it's called. And that gives you the contents of it. What's it like? Yeah, is it like what? Like, it's like a star in C. Contents of it. You know, if you program in C. In Java, they don't have these things. In Scheme, they don't have these things. What the hell? You put dots in front of the variable to get the contents of it. It doesn't matter if you've seen it before. You know what it means. All right. All right. So we are going to reference that x. And when we reference it, we are going to put it in the proper place where it belongs. And what we're going to do is we're going to compute the a. We're going to reference a from the tape in order to compute the description of a. And then we're going to print out a followed by b. All right. Well, how do we compute the description of something whose value is sitting over here? So like in a programming language, the description of a program is usually no more or less than putting that program into a string. The description of this program is just the program with brackets around it. So when I do this computation, Q of b, I'm going to look on the tape, I'm going to put brackets around what I see on the tape, and that will be a description of this program. Now if you're thinking, whoa, what's he talking about? You'll see in just 2 seconds. But maybe I should move on right here. Here, print. Here's where I'm actually going to do something. This part is B. Whatever's going to be on this line is going to go back in there later. Okay, this is the second part. Here's what it does. It's going to print out A followed by B. Well, what's A here? Let me circle A with orange, because it's hard to notice what it is. This is A. That's A. Okay? If I had A all by itself, all it would do is save a description of B on the tape. That's a procedure for A. Now I'm going to write B. What is B going to do? First thing it does is print out a description of A. How does it print out a description of A? It basically puts A in quotes. Now in Logo, there's a particular way to do this. Especially there's some details here. You know, I want this to go to the next line. So these are minor details that depend on the language. But basically, if you do print, it'll shove a carriage return at the end of what you print. And if you do type, it won't put a carriage return at the end of what you do. So I'm going to do print to self. Okay, so that will print out the words to self and then do a carriage return. And then I'm going to type out the words make x. Okay, so far? So see what I'm doing now? I'm doing this part. I'm printing out A.
What's the difference between print and type?
Print puts a carriage return after it's done, and type doesn't. A line feed, not a carriage return. Carriage return and line feed is what I really mean. 10 and 12, right? What if you just send out ASCII 11? Be able to do both. All right. No, it won't. All right, where am I up to? I'm printing out A. So I printed out the first 2 lines of A. I'm just at the hard part.
We also need the open bracket, right?
What?
For make x.
No. We now need to print this part out. Now what is that part? That's the part that's called, what is it? It's the description of B, right? This whole thing with the brackets, including the brackets, is the description of B. With the brackets is a description of B. Inside it is just B itself. With the brackets around it is the description of B. I am now going to right here print out the description of B. Now, do you see here I print out A and then followed by B? In a language it's a little different because B is kind of stuck in the middle of A. You see how A kind of wraps around B? So it's not like you do one and then the other. It's a little bit different than the Turing machine, which would be completely linear on the tape. Here, I'm printing out A. In the middle of printing out A, I have to print out B, and then I can finish printing out A. So right now, I go to this part. I have to print out the description of B. And this is how I do it. I need to just use one long line here, but I'm out of space, so I'm just going to continue on the next line. In logo, you just put like a backslash or something. So there I go. I'm continuing. Print list quote dots x. This is a crucial piece right here. I want a new color for that because it's so important. Green. What is that? What is dots x? Dots x is the thing that's stored inside this bracket. It is B itself. List quote dots x is a procedure just like scheme. It takes two things and it makes a list out of it. List doesn't take one thing, otherwise I could leave out this quote. The quote is like a dummy parameter. It's a minor detail. But list dummy parameter dots x turns the thing inside here into a list. So I read what's stored in here and I turn it into a list. So this whole green thing is actually this whole thing including the brackets. Now you're thinking, why didn't I just store it with the extra set of brackets? That would be this horrible infinite recursion. This is the trick. This is the trick where I don't get this horrible, mirror, mirror on the wall, back and forth, back and forth. This is where I go ahead and take the inside and I put the brackets back around it, and now it's just what I want there. Now it is actually this whole piece with the open and closed brackets. All right, so I've printed that out. That means I've printed out the B. And now all I have to do is finish printing out the A. How do I do that? Well, I'm missing one little thing. Oh, I'm sorry. I'm making this all wrong. Oh. I take back the last 2 minutes of what I said. I'm not up to printing B yet. I'm still printing out A. This part is the end of printing out A. I'm sorry. I just said something completely wrong. I said everything right, but I'm sure I confused you because I confused myself. I printed out to self, type make X, print. I need to print out this part. This is still part of A. So I needed to look at the thing that was stored there, put the brackets around it in order to finish what was A. It's true that the inside is B. There's nothing wrong with what I said, but in printing out this part, which happens to be B, I was really finishing up the printing of A. Let me say that again. I hate to spend a long time on something and then fix it in 2 seconds and go on and just lose all that time. I'm going to say it again from scratch. This part here is what we call B. It is printing out first A and then B. Here it starts printing out A. To self, make X. And now it's got to print out this part. What is this part? This part is whatever was stored in X with brackets around it. So now it's printed out all that stuff, exactly as it's supposed to be. But now, in order to finish up, it's supposed to go ahead and print out B. And B is stored directly in X. And that's what this is going to be. This line prints out this. X here, the dots X, is B. So this printing here prints this whole thing. This is a piece of A. The piece of A that sits here. It equals that. I should have made it green. So all this stuff here prints everything up to here. And this little part at the end prints everything inside here, which is this. It's so cool that it doesn't loop forever. It's just really cool. All right, so what goes in here in the purple?
I still need to print and.
Well, good. Thank you. I still have to finish printing A now. So I do print end. And now what goes in the purple? This. That's B. The purple I just surrounded is B, and that just gets cut and pasted into here. This language is so beautiful to do this in. If I did this in Java, in fact, I'm going to leave a copy of a version of this in Java. It's a holy mess. It's 4 pages long. You got to make a class to, it's just such a mess. You just can't do it so nicely. If any of you can figure out a way to do it in Java in like 5 or 6 lines like this, that would be really nice to see. And maybe you can because you're more fluent in it than I am. But it's just so beautiful to do it here. Scheme also has a 4-line version. Lots of languages. C, of course, has a 1-line version. Of course, it's
0.
Actually, so a lot of people solve this problem by handing in an empty piece of paper and saying, well, here's the empty Turing machine, and it outputs itself. That, of course, is a trivial solution. But right, Perl has a 0-character version. C has a 1-line version, but it's 200,000 characters. This is it. The B is here. The B is also here. Inside the B, we print out the A part that goes up to here, and then we print out the B part. It's staring at you, and it's still hard to get. It's so annoying. It really is. You really understand what Hartmanis said when he said you need to see it when you're 5 to really feel like you completely get it. I mean, there anybody can say I don't get it, right? I mean, there's a million things I can tell you about Turing machines, and maybe you get it, maybe you don't, but who's to check? I mean, how can I really check? I can give you a bunch of homework and get a sense. But here, I mean, I'm going to type this in 3 seconds. Either it's going to spit itself out, or it's going to not. And it's going to work. So it's just so neat. And you can watch it go step by step. Well, you can tell I like this, but I really do. It's really cool.
Is this a strategy that they all use that reproduce?
They all are based. They're all based on this idea.
All viruses use this too?
The part of them that reproduce themselves use this or something which you could probably guess is isomorphic to it. I don't know. I mean, I'm no expert, hacking to every machine I feel like hacking into. I mean, maybe somebody's got a more clever idea of how to reproduce itself, but this is kind of the standard way to reproduce yourself. And you know what's interesting about debugging this? I mean, I spent a few hours last night debugging these things. Every time you make a mistake, you have to change 2 things. Right? Every time you change this, you got to go change that. Otherwise, it doesn't turn out right. So it's very interesting. It's not at all like the programs you're used to working with. It's like you have threads not in the execution of the code, but in the text of the code. And you have to keep them all consistent. Well, what the hell does that mean?
Sean, the other thing about viruses is they don't want to look the same when they reproduce themselves.
Oh.
Part of the point is that they don't have the same signature, because that makes them too easy to find.
Right. But I can make this actually, and I'll tell you in a second. I can make this reproduce itself with a different last line every single time. That's what the recursion theorem really says. It says that you can do anything you want and have the program that's doing it output itself before you do it. That's what the recursion theorem really says. This is a special case. This is don't do anything after you reproduce yourself. The recursion theorem says you could always write a program to do anything you want, including nothing, and before it does it, it reproduces itself. I'm going to say that again, because that is the recursion theorem. A recursion theorem says that if you want to compute anything, you can write a program that computes it, and before the computation is done, your program also spits out a copy of itself. So that's what Michael's saying, and that's what viruses really do. They don't just make a copy of themselves, they make a copy of themselves with some other side effect behavior and with some other signature, which makes them harder to detect. Yeah, it's a good point. And we're going to do an example just like that. Yeah.
If we're going to do an example just like this.
Yeah. And I'm not going to write it on the board. I'll show you it on the screen, because it's really easy to do. But before I do it, I need to go back and write down what the recursion theorem really is formally, because I've just been blabbing about it but haven't written something formal there. Yeah.
Is this like a deep ID in computing? Does this go someplace? It seems like it should. It's like
yeah, well, it's just sitting there in chapter 10 all by itself, which you're not. I don't, no. I would say that if you think of computer science theory as these interesting things, that spiral around and intersect with themselves and spin out interesting applications, and here's compilers, and here's something else, and here's interactive proof systems, and I think this thing just stays by itself in a little island going round and round and round and round. I think in mathematics and recursive function theory it has a lot of applications, but I don't really think that it has a lot of applications in other areas of complexity theory. It's very much a self-contained thing relative to the other stuff we're talking about. And we could have completely left it out of this course, and you would have still had a lot of the basics.
In terms of like living things and machines?
I'm just too stupid to understand that. I don't know. I mean, no, I'm serious. It's probably some kind of deep idea. Look, we're going to do something in a minute, which is a lot more rigorous than thinking about whether this is a deep idea, and I can barely really get my hands around that. And I'll show you what I mean in just a few minutes. I mean, I don't know. I don't know. Now here. Yeah. Oh, sorry, Erica.
Is the reason why you can't print out the brackets in the green box because you'd end up having to backslash them or something, and that would make the whole thing impossible?
Oh, I mean, if I actually went ahead here and tried to do brackets dot x.
That's just a language peculiar. This generates brackets.
Now there'd be quotes if there were brackets.
If you wanted me to do an open bracket and a closed bracket around this and quote them out, that's basically what you want me to do.
Well, that's what I'm saying. If you had to quote them out, then you couldn't end up ever making the thing in the brackets up there the same as the B.
Because there would be brackets in here that would be quoted out.
Right, and then.
I'm not sure what happens when you put quotes inside these brackets. I think we might actually. I'm not sure if we could do that, and I would be happy to actually try to play with it on the screen when we get there. Or maybe if the whole class doesn't want to, I can show you later and we can see if it works. I don't know. I mean, I'm not sure.
Okay.
This worked, and I was glad, so I didn't fuss around. I did try a bunch of other things that didn't work, and every time I went too far down a thread, I'd look at my watch and realize, oh, I got other things to do. I can't spend, the expected 8-hour thread here playing around with this cool thing that I just started. There's a lot of things to try, and I think I would understand it a lot better if I did try a lot of things. Put it this way, I thought a lot about giving this lecture without this stuff, and then I completely decided it was impossible. I really think you have a chance if you see this, and without this, there's just no chance. But with this, it's really worthwhile. Not world class, but still something cool. How's that? A little better? All right, anyway, best we can. Here is the file. It's called self. Whoa, that's ugly. All right, here's the program that we just wrote. Let me separate it from the other one. Forget about self-C. I'll do that in a minute. But here's self. It should be identical to what we wrote here. Right? Make x, print to self, type make x, print list, quotes x, print end. And then the thing at the second line is identical to the thing at the first line inside the brackets. You should be able, in fact, that's how I wrote it. I wrote the second line, and then I just cut and pasted it into the top, just like I described to you there. All right, so now we hit this F2. We define self. I'll put this back up there so we can see it. And now I'm going to, down here, I just write in self by typing it in. And there it is. Isn't that the coolest thing in the world? It's just so cool. All right, so it's just identical completely to what's up there.
It's not colored, though.
I knew I should have turned that damn color off. I was actually just completely neurotic about that. When you use a bigger font, the output goes off the end of the screen. So then it actually puts these little backslashes in to show you, that it really means to be the same line. And then it doesn't look identical to that. And I go, oh, I hate that. It's got to be perfect. So there it is, completely identical. It works, just works, 2 lines long. And it's so much like the way the Turing machine does it. It's so easy to see what's going on compared to the C version, well, the C version is pretty good too, but compared to the Java version.
The little quote in front of the X and make X. Is that just a logo thing?
Yeah, you quote something so that it doesn't get evaluated. You know how in Scheme everything gets evaluated and you put a quote in to stop something from getting evaluated? Same thing in Logo. The dots are a special thing in Scheme, in Logo, that's a little different than Scheme. In Scheme, everything gets evaluated, period. And if it's a value, it just comes back a value. If it's a procedure, it evaluates the procedure. But Logo distinguishes between whether a variable is going to be evaluated as a value holder or as a procedure. And if you put a dots in front of it, it evaluates it as if it's holding a variable. And if you don't put dots in front of it, it evaluates it like it's a procedure. It's easier for beginners. Beginners have a hard time dealing with the fact that the same variable can be a procedure that gets activated and also something that just holds something. I'm sure you all had trouble with that at the first day. Or maybe not. All right, so I'll leave that there for now. I want to explain to you what self-C is. And before I can explain that to you, I need to show you something on the board. But maybe as long as we're here, so I don't shift back too many times, I should show you the C program. You want to see the C program? Mm-hmm. That's one line long also. Where's my C? Borland C. Oh, that looks like hell. Oh, this is it. Oh, it remembers what I did last. How do you like that? All right, so look at this. Oh, you can't see this. Can I make this bigger? I don't know how to work this C so well. View.
It's going to be buried.
Options.
It's going to be buried under options. Go back to options environment. Go back to options environment.
Yeah, that's probably good. Oh, Jesus.
Yeah, it's going to editor. Oh yeah, fonts down.
There we go. Oh, what the hell. All right, if you can see it or not, there it is. It's the whole program's one line long. And look at it. It's very much like what we just did. The first line, the char star s, is a way of storing the string s. That's like make x. And it stores the whole program up until the point where you need to print out essentially the bracketed version of A. And that's done. Do you see the part where it says the first printf S34, S34? Mm-hmm. It's done right there, and it's put in, where is it? This is a little harder to understand. That part gets associated with a %s. That's a little formatting string. And the %s prints that part out as a string. And then that part gets printed out. Ugh. I didn't get that right. There it is. Look at the part at the end. That's the part that actually does printing. First it prints the first string, then it prints a quote, then it prints the string again, then it prints another quote.
It's embedding it in there.
Right.
That's the,
right.
The 34 replaces the %C.
That's right. That's right. Those, right. Right. The last three things there go in the middle of that string. It's a little bit messier than what we did before, but it works just as well. How do I run this damn thing? There. Let me do that first. I think that hits a breakpoint so you can actually see this. No, I guess you can't see it. Can I stop that?
You've got that work.
Well, now it's okay. Now it'll probably work. Hello?
It's running, but there's no...
I want to be able to see it. I can stop it at this point if I hit a breakpoint here.
You had it there before.
Let's try again.
Yeah, go down to the box.
Oh, there it is. It's there. I just didn't...
Yeah, but you have to run
I have to run it again.
Step.
Yeah.
You have to run the first step.
I think it's there now. There it is. Okay? So there's the program. It prints itself out.
There's no return.
No. There's no return there either.
No, there's nothing. There's the include. That's too.
Oh yeah, you know what?
Just added slash n there.
No, I needed to put some 10s in there, or I didn't bother fixing that. The actual version I had didn't have the include standard io.h because it was just done on a Unix system, which just has that in there automatically. And then I did it on this, and it said I don't have the right library because it's C++, and it didn't let me. And then I put it in, and then I realized I didn't have the carriage return. It's an exercise to put in the carriage return, but I didn't have the half an hour that it was going to take me to debug it and do it. You might want to stare and figure it out. It isn't too tough. But whatever you change, you got to change in 2 spots. So there's a C version. Want to stare at it for a while longer, or should we? I can give you a copy of it.
Record for the smallest program.
Oh, people are very interested in things like that.
There's a function.
Everybody wants to write the smallest one in their language. You know, the thing is that you have to be really careful not to write a fake one. Here's an example of a fake one. This is a BASIC program. List in BASIC is kind of like an operating system command which lists a program's listing. So it's fake because it's using the operating system's ability to read this program and print it, rather than the program itself knowing about itself. So when you try to get really short ones, you want to exclude things like this that are cheating. And there's a lot of ways to cheat. I want to go back and put the logo thing back on the screen and show you what that second one is and tell you what the recursion theorem really is. So now we're going to shift back to the board for a few minutes. Are there questions so far? Is it okay? Good? Decent? All right. Let me write down what the recursion theorem really says in real life. Okay. I'm going to talk about a Turing machine called M, and M is going to take two inputs and do something with them. This is going to be abstract again, but I'll give you an example in a minute to make it clear. This is the thing that he said you need to see when you're 5 years old, so be patient. M is a Turing machine that takes two inputs and computes something. It can be anything. It could be like a universal Turing machine, that takes another Turing machine and an input and simulates that other Turing machine on the input. It could be a very simple Turing machine that takes two inputs and just concatenates them together. It could be a Turing machine that takes two inputs and adds them together in binary. It can be anything. So let M be a Turing machine that takes two inputs and computes something. All right, then, here's the recursion theorem. Let's see if I can say it right. Then there is a Turing machine we'll call, what do you want to call it? Call it Frankie. Call it Frankie. I don't know why. I thought I heard Frankie. A Turing machine called Frankie that takes one input Okay, and here's what Frankie does. Frankie of x equals M of Frankie comma x. It looks like it's not saying much, so I'm going to interpret it in English. I'm not going to go through a proof. The proof is very similar to the construction of this, extremely similar. You will gain nothing by me going through the proof and going through this again with one little extra step at the end. So the proof is in the book, and it's very similar to this. But I do want you to understand what it says. So it says, you come up with a Turing machine that has two inputs and computes something. I can come up with a Turing machine, some Turing machine, that has only one input. And if you give it that one input, it'll do what the original Turing machine did, assuming that its first input was exactly the description of this Turing machine. What does that mean in English? It means that this Turing machine, Frankie, is computing what this Turing machine did, but has automatic access to its own description. And it uses it that way. So that's kind of a weird way to put it. Let me do an example. You'll get it with an example. Let me get rid of this. Let's say that M computes MAB equals A concatenated with B. This is concatenation. Let's say all M does is concatenate two strings together. Then what this is saying is that there exists some program called Frankie which takes an input, and what will it output? See if you can figure out. What will it output? What's it supposed to output? It will concatenate X to itself, to its own description. Everyone understand that? If you have a machine that concatenates two things together, then there's another machine that concatenates anything you want to its own description. If you have a machine that adds two numbers together, then there's another machine that takes a single number and tells you the sum of that single number and its own description. So this, if you have a machine that does absolutely nothing, then there's another machine that if you give it anything will take its own description and do absolutely nothing with it. That's what these self-printing programs were. Those are special cases of this theorem. Okay? Let's do one more example besides concatenation. Let's do M computes. M is the universal Turing machine. How about that? That means M of AB simulates A on B. Okay, it assumes it gets a Turing machine and it simulates it on B. What does the theorem imply based on this? It implies that there's another Turing machine called Frankie, that if you give it any string, it will do what the universal Turing machine does with itself on that input.
Basically, it just means it runs.
It runs, right. Right. This is the most trivial example of how to use the recursion theorem. Any program you write happens to work here. It just means it runs on it. Okay? MAB simulates A on B, so Frankie of B is all it's supposed to do is do what the universal simulator does with Frankie on B. It's supposed to run Frankie on B. So whatever it does is okay. Now, as trivial as that is, I'm going to switch this around because this is the coolest thing. M of AB simulates B on A. Okay, it's kind of easy just to switch your universal Turing machine around. Now it simulates the second input on the first input. And now apply the recursion theorem because it says something completely different. What is Frankie supposed to do now? Let's see what this means again. This takes the second input and simulates it on a particular string. Right? So now, it's not the strings that are coming in. It's Turing machines that are coming in as the second parameter is x. And the description of your machine is the string that these Turing machines are going to be simulating it on. So this says you can write a Turing machine that takes other Turing machines as input and simulates it on a particular string. Remember I said this at the very beginning of class? You can take a Turing machine and set it up so that it takes other Turing machines as input and simulates them, say, on the string 0. You can write a Turing machine that takes other Turing machines as input and simulates them on the string 1110111. This theorem says that there is a machine that takes other machines and simulates them on a string so that the string it simulates it on is the same as the description of Frankie. This is saying that whatever Turing machine is working on Frankie, now take a Turing machine, simulate it on something. That's exactly what would happen if you simulated it on the description of this thing. That's the proof of that fixed point. So if you switch this around, you don't get something trivial. You get something completely unexpected. That there's always a Turing machine whose description is exactly the same as the simulation that it's doing of other Turing machines on the given string. So you get that fixed point. It matches. It's really cool. So that's maybe the coolest application that I could think of that's still comprehensible of this. And you can come up with other weird things for M, and then the implications of this become even more difficult to comprehend or maybe philosophical. But what I want to do before I quit, I'll let you stare at this and think about it for a minute. What I want to do maybe just to finish up is let's look at the example for concatenation. The theorem says that if I have a machine that does concatenation, I can construct another machine that concatenates inputs to itself. The proof for that is very much like the self-printing proof we did, except you tag on a little bit at the end and you make sure that you keep track of it in your self-repeater. So let's look at it. Look at this program right here. This program is called self-concatenate. It takes an input this time. It takes a string. And the idea is that it's supposed to concatenate this string to the description of itself, thereby showing an example of this theorem. It's very similar to what we started with. The only thing I do differently is at the very end, after I print out the word end, I print out, see right here? I print out the string. I concatenate it. But look how much I have to change just to put that one line in at the end. Every place that I refer to this line with a parameter, I have to change it. So self-c.string, self-c.string. I think that might be, is that the only thing I have to change?
Well, and the print string must be at the end of that.
And, oh yeah, I got to go off the edge here. And right here is a copy, as I said before. Shit. Come on. Come on. Come on, stupid machine.
The print string must be at the end of that.
And, oh yeah, I got to go off the edge here. And right here is a copy, as I said before. Shit. Come on. Come on. Come on, stupid machine.
Go up arrow once and then go back.
I'm just making this font a little smaller. All right, down it goes. Now you can. All right, up it goes. I'll make it a different.
Just type in 11 and the size. That'll work too.
A little bigger than this. Now I'm cooking with gas. All right, a little better. So I have to put the print string at the end of the program to concatenate it. I have to include that. Remember, any debugging you do in one place, you do in the other place. And I have to change any other parts of it that got changed because of the parameter. And that exercise that I just showed you how to fix that to make this actually do something more than just print itself. The top one prints itself and does nothing. The bottom one does a real recursion theorem example. It prints itself and does the concatenation. That extra part is the easy part of the recursion theorem proof. If you understand the self-reference, that's the hardest part. And here I showed you how to do the extra part. And if you run this thing, self-C test. Oh, that's what I was telling you about those. Sorry, I'm going to do this one more time with a smaller font so you can really believe me. Self-C test. Oh, it still does that stupid thing. I'm not sure why it's doing those backslashes. It's got something to do with going off the edge. But it's exactly the same as what I had up on top. I'll show you what it was. And except for those breaking at the end of the line, it should be identical. And you can see test at the end of the thing. Mm-hmm. You know what? I'm not sure. I think if that part goes past 80 characters, it does this breaking. But I could fix it if I change the font. Take my word for it. Here, I'll do it. Don't take my word for it. I'll put it back to here, and maybe, well, now if it doesn't work, you're never going to believe me. Yeah, maybe you will. Oh, don't believe me.
There's a little turtle on the screen.
Yeah. You want to see a logo's fun. I was going to actually do this. Instead of concatenation, I was going to have a program that made a circle, and then this program was going to reproduce itself and put a circle around it. And I said, I only got 10 minutes here. I gotta make it clear. All right, so that's a minor thing. Those backslashes are because it goes off the edge of the line. It just means it's not an important point. But it really does reproduce that program exactly. And we could do this theoretically. No matter what the computation is, we can create our Frankie.
And this also means any computer language you can do this with.
Yes.
In theory.
Yes. Doesn't matter if it's Logo or Scheme or Java or Forth or Haskell or who knows what. It's the coolest thing. Yeah. But it's really just a cool thing. I mean, go hack around. There's a page called Quine. These are sometimes called Quines, named after the logician, I guess. And these self-repeating programs. You can find a page that just has hundreds of these submitted. And with various testimonies of various programmers and hackers who got their original interest in their career because they stumbled on something like this. They thought it was just so cool and so ingenious, and then they became programmers for the rest of their lives. So some people actually got inspired by things like this.
I'm just wondering what's the basic difference that lets the barber not be able to shave himself, but the
But the program able to?
To print itself.
I'm not even going to attempt to answer. I just don't know how to. I don't have a better answer better than just look at that example again. I really don't. I don't have a really, really inner feeling as to the difference. And I might one day, and then I'll try. And it's like a teacher's worst. I was talking to Patrick Winston about this. He goes, you know, whenever you go to a class, you always tend to have this disease that you never feel you have enough. You know, and that happens when you think about something for 20 years. It starts to seem easy, and you feel like, well, I'm going to be done in 10 minutes. So you prepare more, and then if you don't catch yourself and have a little self-awareness, you'll lose it completely. And it's like, one day I will finally get an idea, and then I will be like compelled to have everybody understand it in one afternoon. And it'll just be, I really don't have anything to say, and I wish I did. I just don't have a nice explanation.
These machines are not universally aware. They don't have to deal with
That's right.
world of truth.
That's a nice thing to think. Right. They certainly only deal with themselves. Right. We're not talking about a collection of people in the city and that one person knows everything about all the other people in the city. We're talking more that any particular person in the city is allowed to know a lot about themselves, but maybe not a lot about everyone. So I think that's a nice way to put it. Yeah, that's a good idea. Yeah.
Except that the problem was with the self-knowledge.
Yes, the problem with this, right. The problem with knowing about everybody is self-knowledge. But if you don't insist on knowing everything, then it's okay to have a little self-knowledge. I guess that's the moral. A little self-knowledge is a good thing. All right, good. Tom's here, so he's still taking pictures of me, right? I want to finish with this topic, and I'll give you copies of all these things that I have, and I'll let you look at them and play around with them. But I want to do one more short topic before we go, and it's something you've seen before, and the only reason I'm doing it is because it's just really cool, and I don't have to get into too many details about it. So I promise I never put the picture on the board again, but I'll just put this one word on the board. Imagine the picture's there, and one of the rings says p-space on it. And remember I told you that p-space equals a time, alternating time, that's polynomial. So if you have polynomial time algorithms, but they work on alternating Turing machines, that takes us all the way to p-space. Non-determinism takes us out of p into np, and alternating, the next step up, takes us up to p-space. Nice little jumps. There's something else that p-space is equivalent to, a class that I haven't talked about at all. It's really an advanced topic, but Mike Sipser talked about it when he was here. So I'll be able to remind you fairly quickly. I won't go into any formal details about this class. I'll just give you an example of how you compute things in this class. And then I'm going to tell you the theorem that this class, which is called Interactive Protocol, that this class called IP, is exactly the same as p-space. And that's just the kind of results theoreticians love. Somebody makes up this weird class, hopes it's a natural class to make up, and somebody else shows that it's exactly the same as another class we've been talking about that has a natural meaning. This is a very wonderful theorem, and it's a long one. It's about 10 pages in the book. So I won't convince you of this theorem, but I do want to tell you what IP is. So you know what p-space is. You know what A-time poly is. P-space is deterministic algorithms that use polynomial space. A-time poly are polynomial time algorithms that use alternating Turing machines. Interactive protocol is not at all like any computation you've had so far. It's not exactly deterministic. It's not exactly non-deterministic. It's a conversation. We compute things by having a conversation. Now, non-determinism in some ways is like this. In non-determinism, we have a very short conversation. Say I want to figure out 3-sat. How do I solve 3-sat non-deterministically? Who remembers? What do you do?
Make a guess.
You make a guess as to what? What do you guess? A truth value for every single variable. So let's say that's your part of the conversation. Erica picks true and false for all the variables, and then she sends that message to me. And I got this letter from Erica, and I'm opening it up really eagerly, and in it is nothing but true and false values. And I go, and then I look at it, and I say, well, I wonder what she's doing with her life, but let's at least check whether this formula is satisfiable. So I look at the formula, and I check the true-false values against my formula, and it works out. And I write her back a letter, and I go, thanks. Now I know this is satisfiable. And then she sends me a note the next day with another true-false assignment for a different formula that I had sent her. And that one doesn't work out. I go, can you please try again? But she can certainly convince me that it's satisfiable when it is. All she has to do is guess a way to do it, and I can evaluate that in polynomial time. So my job is a polynomial time evaluator or verifier. And her job, I don't know how she does it. She has superpower. You know, I don't measure how much time she takes. Her job is to convince me of these things. Think of non-determinism that way, and you'll understand a little bit about interactive protocols. Interactive protocols are the same kind of thing, except there's some randomness involved, and there's a back and forth that can go more than once.
This is Sipser's lazy slave thing.
Exactly. Right? It's the same thing. It's not. You've heard it before if you were at the lecture, and if you weren't, you'll hear it now. What about the complement of 3 set? I have a formula, and I want to know not whether it is satisfiable. What I want to know whether it's not satisfiable. Everyone understand the difference? And Erica's sitting at home, and she gets to send me these same messages, and I get to check them in polynomial time. How can she do it now? If she sends me a true-false set of values, and I check to make sure that they don't work, am I convinced that there's no assignment? No, because there might be some other one. So she'd have to send me another one, and another one. How many would she have to send me until I'm convinced that there's no 3 set? All of them, all 2 to the n. So despite the fact that she has tremendous power in picking these things, and she can, I don't measure how much time it takes her, but the protocol constrains us for this problem that I can't do it any better than 2 to the n time. She has to send me 2 to the n messages for me to be convinced. This problem is not in NP as far as anybody knows. Complements of NP is not closed under complement. This problem is NP, and this is not an NP. P is closed under complement, but not NP. Can't do complement of non-deterministic stuff, just like finite state machines. So Erica can't do this. So what people did is they said, well, why don't I just invent some way to improve the protocol and allow people to convince other people of things like this? And the best way to explain this protocol is to explain an example of a very famous problem called graph isomorphism. We talked about this once also. Graph isomorphism is a problem where you're given 2 graphs, G1, G2, and you're asked, can you place one on top of the other so that all the edges match up? Are they really the same graph for all intents and purposes? Can you relabel one so that it matches the other? Now, if you try to do that by brute force, deterministically, it takes n factorial steps. You have to try all n factorial ways of ordering the vertices and then checking the edges to see if they match. But now we'll do the same thing. Erica's a non-deterministic prover, and I'm the verifier or the evaluator. How could she convince me whether 2 graphs are isomorphic if they are? She guesses an ordering of one of them, sends it to me in order, and I compare it with my current ordering I have on the other. And if she's powerful enough to find the right guess, then I'm certainly powerful enough to check it in linear time, time proportional to the edges. So this is a problem that's in NP. Okay, you can guess it and check it. Its complement, just like the complement of 3 set, is not in NP. If you want to convince me that 2 graphs are not isomorphic, you'd have to send me all the possible n factorial arrangements, and I'd have to check them all to make sure they don't work. Same as before, this is an NP, the complement's not an NP. You should know one really cool, interesting thing. Most problems that we've talked about are, when they're in NP well, typically you try to show they're NP complete. Very often, you have a problem, either you stick it inside P, you show it's polynomial time, or you show it's NP complete. You don't like to leave problems sitting in open land. This problem has been in open land for at least 25 years. Nobody has any idea whether it's NP complete. Nobody has any idea how to do it in polynomial time. So it's one of the few problems that are not the hardest problems in NP. Almost all the problems in NP that we know of are at least as hard as all the others. This one might be easier as far as we know, but nobody knows. Wide open, this problem.
So it's reducible to NP complete problems, but not the other way around?
That's right. This reduces to any NP complete problem, but not any NP complete problem reduces to it as far as we know. So it's at least, they're all at least as hard as it, and we don't know if it's as hard as they are. But we think it is. Just nobody's come up. I think this just shows that NP complete is a weak theory. It's not enough to get everything that's hard to do. There's other kinds of things that we await people to discover. All right. Let's think about the complement of this, because the complement of this problem is one where we can make up a protocol where you as a group can convince me that two graphs are not isomorphic. But we need a protocol to do it. And this protocol is different than the normal non-deterministic protocol. It's a protocol which is part of a larger computation style called IP. Okay, now here's the conversation we're going to have. There are two graphs, G1 and G2. I want to be convinced that they're not isomorphic. We're going to do graph non-isomorphism. No way to do this in non-deterministic polynomial time, but there is a way to do it in this style. I want to be convinced they're not isomorphic. I want you to help me. You can provide me with guesses, with information. I can verify that information. I don't necessarily trust you, but I'll check whatever you give me. And I'll try to use the information you give me to convince myself that these are not isomorphic. So if I ask you for an ordering of a particular graph, I get nothing from that. I'd have to do that n factorial times to get anything from it. But here's what I'm going to ask you to do instead. I'm going to ask you to do me a big favor. Well, and this. I'm going to take one of these graphs at random. I'm not going to tell you which one. I'm going to reorder its vertices. Let's call that graph H. It's either G1 or G2 all mixed up, because you guys have a copy of G1 and G2. I'm going to mix one of them up. I'm going to call that H, and I'm going to send it to you. Okay? And I'm going to ask you, is H equal to G1 or is it equal to G2? Everyone understand what I'm doing? We'll see why I'm doing this in just a moment. But make sure you understand the protocol. So we can have a conversation back and forth now. I don't just wait for you to give me information. I give you something to do, and you give me back information, and we go back and forth, and there's some rolling of the dice here, too. The rolling of the dice is that I rolled some dice to decide which one of these I was going to send you. I get to do random stuff. You don't get to do random stuff. I get to do random stuff. So I pick this randomly. It gives me power to do random stuff. It's amazing how much power it gives me. I pick this randomly. I hand it off to you. I randomly redistribute the nodes, and I say, which one is it, G1 or G2? And you sit there, and I don't care how much time you take or what you've got under your sleeve, you're going to give me some answer. Now let's say it's really G1, and you get it right. You say it's G1. Well, you had a 50-50 chance to get it right. So that's not a very big deal. But let's say I randomly choose back and forth between these two, and for 50 times in a row, you get it right. The chance of that happening, if you did your guess randomly, is 1 in 2 to the 50th. That's the chance of you getting every one of those right. So there's no way you're getting it right randomly. If you're getting these right, if I have a 50 mail back and forth with you, and you get it right 50 times in a row, I can be certain, virtually certain, not certain, virtually certain, 99.999%, with only the teeniest chance of an error, I'm virtually certain that you did not randomly just pick G1, G2 and send it back to me. Well, how could you know whether it's G1 or G2?
If they get it wrong, that means that they're isomorphic.
No, it doesn't mean anything if they get it right or wrong in a single time.
If you send them G1 and they match it with G2,
they're matching it with H.
Yeah, they're picking.
They're saying that H came from G1.
Yeah, but what if they show it comes from G2? Doesn't that mean that G1 and G2 are equal?
Yes, it does.
Yes, okay.
Yes, it would. Right. So let's think of the possibilities here. Let's say these two really were the same. Then how would this protocol go? I pick one of them at random. I send it to you guys. And you tell me which one it is. You can try your hardest to mess me up. But how are you going to possibly know which one it was if these two are exactly the same? The best you can do is random then. So what you asked, Neil, what if they're the same? What if they are the same and I do my protocol? Then I will never expect any answer better than random, because you don't know which one it came from. And it could be either G1 or G2. Whatever method you use, you're going to have to guess sooner or later. So if they are the same, I expect random answers from you guys. Therefore, when I get an answer like this, where you got 50 in a row right, you've convinced me of something. You've convinced me that they are probably not isomorphic. When they are isomorphic, you can try as hard as you want, and you'll never convince me of anything. But if they are not isomorphic, you can definitely convince me that they're not isomorphic by getting the answer right a lot. So this protocol is different than non-determinism. For one thing, I have random choices that I can use. Flipping a coin, and that gives me a lot of power. For another thing, I get repeated conversations, not just a one-time letter. We get to send letters back and forth 50 times. It's the repetition of the letters and the use of the randomness that gives this protocol more power than NP. And completely fascinating and interesting, it picks it up exactly one complexity class, moving it from NP into P space. Everything you can do with this protocol, you can write a deterministic polynomial time algorithm that uses polynomial space algorithm. And if you have a polynomial space algorithm, you can come up with a protocol, a conversation like this, which solves it just as well. They're equal. So that's one of the really beautiful results in complexity theory. And this is new. This is not new. It's 10 years old, probably. Certainly within the last 10, 15 years. OK, I'm going to quit with that. Other questions about anything?